The topic of my presentation today is actually a part of my ongoing research and also my past research that I really actually started during my promotion in Freiburg in the first chapter of my dissertation some 20 years back. And what I tried in this dissertation or in the first chapter is to explicate one of the basic principles of infinitesimal Rechnung as discussed in Hermann Cohen's seminal work, Das Prinzip der infinitesimal Rechnung und seine Geschichte, which was based on Kant's Antizipation der Wahrnehmung, the anticipation of perception in Axiome der Anschauung, in Critique of Pure Reason. And Cohen was trying to equate the intensive Größe, how Kant explicates in his work, with the dx. And then my premise was actually another work of Dmitry Gavronsky, not a well-known philosopher of mathematics, but Dmitry Gavronsky studied in Marburg under Hermann Cohen, and he belonged to the Neukantianer in Marburg, Marburger Schule, along with Cassirer, Nator, and Cohen. And he wrote a dissertation under the guidance of Hermann Cohen with the title das Urteil der Realität und seine mathematischen Voraussetzungen. And for me, it was a very a wonderful coincidence that I discovered a copy of this dissertation in Freiburg Library. And I searched for further copies and found out this was the only copy in the entire Germany. So I started with that dissertation. And in this work, Gavronsky discussed mainly the principle of infinitesimal Rechnung, the differential calculus, with various theoreticians, mathematicians, and philosophers like Cohen, Kant, Cantor, Lagrange, Leibniz, Newton, and many others. And in today's presentation, I just want to highlight what Dmitry Gavronsky problematized in his dissertation, which is the process and its limits, and whether the limit emerges out of the process or the limit is something that we have to set as outside the process, something like that. So the main discourse was, as that relates to the principle of differential calculus, is about what is continuity, continuum. So that was the discourse, the continuity and the discretion. So within the context of differential calculus, the continuity is discussed in various frameworks, like in algebra, geometry, and arithmetic. And obviously, introducing continuity in geometry means introducing movement in geometry, which was at that time disputed or debated widely in Europe. And with the advent of analytical geometry, which somehow synthesizes, as Panofsky observes, the algebra, arithmetic, and the geometry. And this principle of continuity relates to all the fields of mathematics and the arithmetic, geometry, and the algebra. So the question is whether we can admit a discretion in the continuity, or continuous or continuum is something that surpasses any discretion, that doesn't allow any discretion within a process. So that was the debate, and as is well known, this principle of continuity by Leibniz, or principle of continuity as a fundamental philosophical principle, produced in the mathematics the wonderful tool of differential calculus. So there are two origins. Apparently, the one is the Newton flexions, which he derived from the dynamics, and the Leibniz deriving the differential calculus, the most fundamental procedure of differential calculus, partly from a philosophical principle and partly from the geometry. So, and then that inaugurated a long debate on the infinitely small and infinitely large quantums, whether unendlich kleine or unendlich große, whether they are possible in reality, or can that be admitted in mathematics? And also this continuity and the discussion, uh, the conflict between these two, as is evident that the differentiation has to somehow overcome the philosophy of differentiation and become a bit more pragmatic, and then legitimize the infinitely small as a discrete entity so that integration is possible. So integration is the summation of final entities, and these final entities are infinitely small entities. That's how the differential calculus, along with differentiation and integration, function. So there is not just a logic or theory, but more pragmatism in the advent of the differential calculus in the history of mathematics. So I'll just share a few quotes or observations by Gawronski in his dissertation, and these are I'll read it out, and that introduce the problem of continuity and the discretion to some extent, and also along with the necessary references from philosophy and mathematics. Ja, this is from his dissertation, Das Urteil der Realität und seine mathematischen Voraussetzungen. Das eigentliche Problem des Kontinuums ist das Problem seiner Erzeugung. Wollten wir aber zu diesem Ende von der Bestimmung eines Mittleren ausgehen, indem wir es fortwährend interpolieren und diesen Prozess der Interpolation ins Unendliche fortsetzen, so wären wir niemals imstande, auf diesem Wege durch diesen Prozess, er mag sich auch noch so weit erstreckt haben, das Kontinuum hervorzubringen. Die unendliche Teilbarkeit und die Fixierung der Teilungspunkte, mit der wir hier zu tun haben, genügt nicht, um unser Problem zu lösen. Diese unendliche Teilbarkeit ist in der Tat nur ein Symptom, eine Eigenschaft der stetigen Größe, nicht aber ihr Erzeugungsprinzip. Als solche, das heißt als immer fortdauernde, setzt sie schon in diesem ihrem Begriff des Immerdauerns voraus, dass sie niemals durch alle Punkte hindurchgehen kann. Denn dann wäre es mit ihr zu Ende. Durch die Fixierung dieser Punkte hatten wir also niemals ein Kontinuum, sondern immer nur eine lückenhafte Extension erhalten. Daher ist doch die Definition der Kontinuität, die Kant gibt, so wenig befriedigend. Die Eigenschaft, die dieser Definition ist, die Eigenschaft der Größen, nach welcher an ihnen kein Teil der kleinstmögliche, kein Teil einfach ist, heißt Kontinuität derselben. Nein, diese Eigenschaft kann nur eine Folge oder Symptom der Kontinuität genannt werden. Sie macht aber nicht ihr Wesen aus. So what he basically tries to problematize here is the existence of any part as a final entity, as a discrete entity within the continuum, as normally represented in the Zahlenreihe, the row of numbers increasing, or a geometrical process, the movement or the construction of a line and a variable in algebra. And in all this continuous process, Gawronski argues we cannot admit a discrete entity. So it has to be continuous. It's almost like lückenlos. and without any gap. So he gives further references from Ernst Cassirer and how Cassirer tries to analyze this, and by emphasizing the process of integration, which again Gawronski negates. Es muss also eine Cosa Continua, eine Continua Generatio gefunden werden, die die Erzeugung der stetigen Größen auf sich nehmen kann. So löst sich für Leibniz, wie es Cassirer ausdrückt, das Problem des Kontinuums in das Problem der Kontinuation auf. Das Gegebensein des Kontinuums wird in dem Verfahren der Kontinuation aufgehoben. Denn es wird aus ihm hervorgebracht, das Prinzip der Kontinuation ist aber nichts anderes als der methodische Ausdruck der Integration, als der stetigen Summierung der infinitesimalen Elemente. Diese Bestimmung der Kontinuation kann indessen auf den ersten Blick wohl weniger befriedigen. Die Lösung, die in ihr unserem Problem gegeben wird, erscheint als eine bloße Tautologie. Das stetige Sein wird durch das stetige Summierung ersetzt, wird aus ihr hervorgebracht. So he points to the principle of the production, the creation, Erzeugung, which cannot allow the summation of final discrete entities. So, which is the principle of integration. So the Summierung der infinitesimalen Elemente, and which clearly suggests a discrete final individuation of the infinitesimal, and this Gawronski negates, and then he moves to a kind of solution to this problem in the concept of limit. So then in this quote, he gives a historical account of the problem of infinitesimal. So what happened with the infinitesimal in geometry and mathematics, and the discovery of infinitesimal Rechnung, the differential calculus, as we all know, it was widely disputed in Europe, and by George Berkeley in his polemics in Analyst. And so it's more of an ontological problem. How can the infinitely small or infinitely large exist? And especially the infinitely small, which is the foundation of differential calculus, that somehow escapes our perception, because there can be differentiation of any order. So the d by dx, d dx by dx, d dy dx, etc., etc. So it goes on. And interestingly, most of the mathematicians and the philosophers never accepted the individuation of infinitely small, but then tacitly admitted that in the mathematical operation and its development in the history. So there is a kind of paradox in that. So es wird hier mit unendlich Kleinem operiert, aber auch mit unendlich Großem. Was aber ist denn eigentlich, wenn diese Prädikate zukommen, dem diese Prädikate zukommen? Man hört oft sagen, es sind unendlich kleine und unendlich große Größen. Aber sind solche Dinge überhaupt möglich? Ist vor allem eine unendlich kleine Größe möglich? Leibniz, der Entdecker dieser Analysis, bestreitet es aufs Entscheidendste. Dasselbe tut auch Lagrange, der eher bereit ist, die ganze Rechnung mit unendlich kleinen Größen aus der Mathematik zu verbannen und sie für durch und durch fehlerhaft zu erklären, als im Gebiet der exakten Wissenschaft ein solches Unding zu dulden. Und nicht anders steht es bei Krelle, bei Cantor, bei Stolz und vielen anderen. Ferner, das unendlich Kleine ist hier in Beziehung zu endlichen, wenn auch sehr kleinen Größen gesetzt. Diese Größen haben jenes unendlich Kleine zu ihrem Grenzwert. Aber wie sollen wir uns diesen Grenzübergang denken? Woher sollen wir die Mittel nehmen und worin sollen die Mittel bestehen? Die Imstande wären, eine endliche Größe dieser ihrer Eigenschaft der Endlichkeit zu berauben und sie in eine unendlich kleine Größe zu verwandeln. In fact, this was not a new discourse in the history of mathematics. Um, it's already there in Aristotle. I mean, the actus and potens, so the actual and the potential. So for Aristotle, there cannot be an actual infinitely small magnitude. An infinitely small magnitude has to be conceived in a process that is as potential. So it's not that infinitely small, it is infinitely diminishing quality. It's a kind of participle, a process well. In a process, we have to think because there is no discrete finality. There is no end to this process. And this surfaces again and again in the history of, in philosophy as well as in mathematics, and finally found its practical application in the differential calculus. So Gawronski then moves to a plausible explanation of this problem by separating the process from the limit. Now, obviously, the limes, the limit, is a final discrete entity. It's a discretion. But then he argues this limes cannot emerge from the process. So the process tends to this limes, but still this limes is some, for the limes we have to set another principle. So that cannot be derived out of the process. And the process here means the arithmetic process or the dynamic processes or the geometrical process, the movement that is introduced in geometry, etc. But in my investigation, I focus on the dynamic process, and the dynamic process, how it tends to a static limes. So here, this is the final quote. I mean, not the final quote. I mean, the last observation from Dmitry Gawronski that I quote from his dissertation. In der Tat betrachten wir genau das Wesen des Grenzübergangs. So this Grenzübergangs has different references. So he primarily refers to Cantor, who had a kind of conception of the infinite series, like the infinite process, which always pass over the discrete limits. So it's a kind of wandering limit, and which also Gawronski negates or questions. So in der Tat betrachten wir genau das Wesen des Grenzüberganges. So erblicken wir in ihm einerseits den Prozess, den unendlichen stetigen Fortgang, andererseits aber den Grenzwert, zu dem dieser Vorgang fortstrebt. Woher kommt aber dieser Grenzwert? Aus dem Prozess kann er nicht entstehen, denn der Grenzwert ist doch das mathematische Ende des Prozesses. Er steht in handgreiflichem Gegensatz zu ihm und kann somit aus ihm nicht entspringen. Nein, zum Grenzwert kommen wir nur, wenn wir eine neue Setzung zu vollziehen uns erkühnen, wenn wir neben dem Prozess und unabhängig von ihm ein neues Prinzip in Tätigkeit setzen, welches die aktual, die tatsächlich vollzogene Sitzung des Unendlichen hervorbringt. In fact, I started with this. I want to start with this quote, so then I translated it. The previous quotes, then I added to it, just to explain the problem of continuity and discretion as a kind of propedeutic to my talk. Indeed, if we look closely at the nature of crossing the limit, we see in it, on the one hand, the process, the infinite, continuous progression, but on the other hand, the limit to which this process tends. But where does this limit come from? It cannot arise from the process, because the limit, which is Grenzwert, is the mathematical end of the process. It stands in tangible opposition to it and therefore cannot arise from it. Now, we only comes to the limit if we dare to carry out a new processing, if we put into action alongside the process and independently of it a new principle which produces the actual that actually carried out processing. What I'm trying to demonstrate is exactly the opposite. And it's not that we set a different principle for the limit, which is done in the procedure of the foundational procedure of differential calculus. So I don't deny. But actually, the process, in fact, the limit emerges out of the process, even though the limit does not belong to the process. So uh, why this was ignored or overlooked? Because um, geometry and also the arithmetization of geometry in the context of analytical geometry, this all happened primarily in the framework of space. So it was the spatial reduction of movement and time. And the time and movement in its pure continuum, pure continuity was never considered in the foundational procedure of differential calculus, which I'm going to explain now. So then to introducing in the introductory part of the differential calculus, this is the famous principle of continuity from Leibniz. Kontinuität zeigt sich aber in der Zeit der Ausdehnung, den Qualitäten, den Bewegungen, überhaupt in jedem Vorgang in der Natur, der niemals sprungsweise geschieht. So, as I mentioned earlier, so here the Leibniz would be the best example how he had a kind of ambivalent thought process when it comes to the principle of infinite differential calculus. So in the philosophy, he represented or he had this principle of continuity, which never allows a discrete sprung or a discrete state or a discrete individuation. And because there is no sprung, a jump from a pure static to a pure dynamic. So this dynamic process has to be continuous without any discrete elements or parts in it. And this was conceived not in an intellectual imagination, but in the nature itself, so in the materiality. So this is the foundational principle of in differential calculus for Leibniz, but what happened was in the actual practice, in the derivation of the foundational procedure of differential calculus, he tacitly admits the discretion of the continuum in the infinitesimal in dx. And otherwise, the process of integration would not be possible. So there is a difference between theory and pragma. So in the history of, and particularly in the genesis of differential calculus. So now it's a very interesting geometrical demonstration of the principle of differential calculus in one of the early works. I can't remember, this could be before the introduction of differential calculus or after that. So anyway, this was published or edited by Ernst Cassirer, the Hauptschriften zur Grundlegung der Philosophie. This could be the first time the movement was introduced in the modern geometry. Of course, there are other examples of this prototype of movement in geometry in Nicolaus von Cusa, which I'll explain later. So this is a geometrical demonstration by Leibniz in a method in the form of a certain aporetic or a reductio absurdum in order to prove the necessary existence of infinitesimal. So there were a lot of polemics against Leibniz by Berkeley and by many others, by Gauss also later, that how is it possible, I mean, an infinitely small as an existing entity in mathematics. So here, Leibniz is trying to demonstrate that if we don't admit the infinitesimal in this demonstration, and it leads clearly to a irregularity or a problem, a logical problem. So there are two lines here. This is AV and EY. Well, I'm not going to read the code, read directly from his text, so I'll just explain how he demonstrates. So the two lines, AV and EY, intersects at C. One second, I'll just... yeah. Um, yeah, these two lines intersects at the point C, and if you draw perpendicular bisector from the line AV to the point Y and E, so you get CXY and CEA, two triangles, similar triangles, whose sides are proportionate. Like if AC is C and AE is E, C is to X minus C, that is this side, is same as E is to Y, or C by E is equal to X minus C by Y. And then another assumption, this angle, this YCX or ACE is not equal to 45 degrees, is less or more than 45 degree. That means C by E or X minus C by Y is not equal to 1. So these sides are not equal. So these are the assumptions, or these are the premises. And then the Leibniz introduces movement in this model. So the line EY moves or shifts parallelly to the point A, and which almost form the limes. So it moves to the point A, and as a result of which these two magnitudes, C and E, become smaller and smaller, and this triangle, ECA, becomes smaller, vanishes in a way, but still maintaining the proportionality, which is C by E is equal to X minus C by Y. But then he argues, suppose if this line, E dash Y dash, I'm sorry, this is, 1 second. This is the one. So suppose if this line E dash Y dash reaches the point A, what happens? Both these magnitudes, E and C, vanish. So C by E is then 0 by 0, which is for Leibniz 1. But as we know that any division by 0 is infinity, but that is not the issue. When these two magnitudes vanish, the original proportion that C by E is not equal to 1, or X by Y is not equal to 1, does not hold. So that's the problem. So in fact, this is an aporia if we think this process in geometry. But if it were in mechanics, so we obviously know that one of this magnitude is C is larger than E. That means the point C will move faster than the point E. And finally, both these points will coincide at the point A. So there is no problem if it is mechanical, a dynamic process. But in the geometry, which is again based on the division of this magnitude, there is a problem, because in order to maintain this proportionality, the C and E have to exist, and it should not vanish at the point E. That means the C and E should exist as infinitely small. And even if it reaches A, there should be an imaginary triangle at A with infinitely small sides, C and E and EC. So, and obviously it refers to the polemic by Berkeley, who say that there cannot be a triangle at a point, etc. So now, there is an aporia, a geometrical aporia here. However, through the introduction of a dynamic process, movement in the geometry. So now, if to maintain this triangle, what is not specified in this demonstration of Leibniz is the nature of the movement. So he says that this shifts to A and pass through A. And obviously, if it passed through A, there won't be any entity like C and E because at A, both these magnitudes vanish. And if it's for example, there are three modes of movement: a uniform movement, an acceleration, or a retardation. If it's a uniform movement or an acceleration, it will definitely pass through A. So the only possibility to maintain the triangle ECA and or the sides E and C, or to guarantee their existence as infinitely small, is that this movement has to be a retardation. Not any form of retardation, but a specific form of retardation. That means the E dash and Y dash approaches A infinitely, but never reaches A, forming these infinitely small quantities. And this is exactly what I want to say. And based on this most primary demonstration of Leibniz. So I try to revise this model a bit. Suppose if there is a limit like E dash dash and Y dash dash through A, which is the limiting limes of this movement, and then E dash Y dash moves the line EY, which moves towards A, and the the diminishing infinitely small quantities would be delta E and delta C, and also the EC, delta EC. And I also try to think in terms of time, that there should be a delta T as an infinitely small uh, time, or a temporal entity, uh, and before this between the limes and this line. But the problem is, because it's an infinite movement, delta t is not just not infinitely small, but an infinity itself. So, and as a part of temporal differentiation, and which is a different subject. So there is a final triangle, which is a delta E and delta C as two sides, but still in a process of diminishing or vanishing. So, but the problem of this solution is obviously the C and E are not equal. So if they are not equal, the delta C and delta E are not equal. So there are two different infinitely small quantities, which is a contradiction, because the definition of infinitely small is a magnitude greater than zero, but there cannot be a in-between magnitude between zero and infinitely small. So again, we are not solving this aporia, but we are only adding a different aporia to this geometrical model. But in any case, the existence of delta E and delta C presupposes the movement, the retardation of this movement. And my argument is, of course, this mirrors, reflects the foundational procedure of differential calculus, where one point moves along a curve to another point. So my argument is, this process should have a singular mode of retardation, and only in that, provided if we set the limit as I mean in advance, so then define the process. There is only one possibility, the one possible mode of movement, which is a particular form of retardation. So then, based on that, so we can easily understand this the first method of differentiation, how it was introduced. And this is not exactly the Leibnizian or the Newtonian method, but then it's derived from them, and which you will find in any textbook of differential calculus. So here we have a curve, and the point P moves to Q, and like P is xy, then Q would be a kind of a suvax, a small increment of delta y on y-axis and delta x on x-axis. So delta yx plus delta x and y plus delta y. So then the point Q moves back to P. So that's a movement that is introduced in this procedure. Thereby, this delta y and delta x diminish, becomes smaller and smaller, and delta x tending to 0. But it's only tending to 0, it never becomes 0. That means the Q reaches P, but it never reaches P. It cannot pass through P, because if it passes through P, then delta x becomes 0 and then negative values it can take. So which is not possible in this method. So here again, the delta x tending to 0 necessitates a particular mode of movement. So this is exactly what I'm trying. So we have to take into account the dynamic process in this foundational procedure of differential calculus, which was never done. So now the question is, how is it possible that an infinitely small quantity of delta x or later dx is produced at this point P? It can only be produced when this movement is clearly specified as a retardation tending infinitely to the point P, which we already know. So, but somehow this dynamic process was never considered because the movement was introduced, but then nobody cared about whether this is a uniform movement or an acceleration or a retardation, as far as I know. Maybe there are attempts to analyze that. So it is clear that the limit dy by dx, delta y by delta x tending to 0, this delta x tending to 0 clearly suggests a definite process of movement. And my argument is the limit, this point, emerges out of this movement. And now the question is it possible to accommodate this dynamic process within the context of geometry, or to admit or legitimize this dynamic process and its limits, which emerges out of the process in the foundational method of differential calculus. So I just, how do I say, sorry, this is 1 second. This is from my dissertation. I try to speculate a form of temporal differentiation by introducing delta t, but of course the time was already introduced in the differential calculus, but with a reduction to a spatial entity and not as pure time and pure or a pure movement. Yeah, so as time demonstrates in a movement, is demonstrated in a movement. So in the formal dy by dx, limit delta x tending to 0, delta y bei delta 6, das ist aus dem ursprünglichen geometrischen Verfahren der Differenzierung ableiten lässt, wird das rein operativ kontinuierliche durch d bei dx, den Operator, und durch delta x tendiert zu 0, die Operation dargestellt. Wenn im Kontext der Differenzierung die Operation der unendlichen Verkleinerung räumlicher Extension, nämlich delta x tending to 0, der Operation der unendlichen Verkleinerung der zeitlichen Dauer, nämlich delta t tending to 0, analog ist, because delta x tending to 0 in the final instant, that when delta x is infinitely small, it's equivalent to delta t tending to 0. Kann das hier eingeführte Faktum der variierenden Zeit Die Variable x, die in dem ursprünglichen geometrischen Verfahren der Differenzierung die Variation der räumlichen Extension darstellt, entweder ersetzen oder bloß supplementieren. Demnach lässt sich die ursprüngliche algebraische Formel der Differenzierung folgendermaßen umformulieren, which is dy by dt is delta t tending to 0, delta y by delta t. Then you add the spatial entity, the dy by dx dt, delta x tending to 0, delta t tending to 0, delta y by delta x, delta t, etc. But this is, I don't know, I mean, I'm not a mathematician, and I could not really complete this process. Yeah, so this is just an attempt to incorporate the factum of pure time in the process of differential calculus. The problem is then it is not like differential calculus as the foundational tool for applied sciences like mathematical physics. So this becomes a physical mathematics, and which is till date not really recognized in the domain of mathematics, or whether it is possible that there is a physical mathematics incorporating the factum of time and movement in the differential calculus. So now I'm trying to extrapolate this process limit problem into an old or very primordial discourse or primary discourse on this process limit, namely the Cenos Paradox. And as we all know that it was this whole process, the problem of infinite process and limit was introduced apparently in Cenos Paradox, and at least in various attempts to solve the problem. So this is actually from the first chapter of my next publication. It will be published in April from Carl Alber, and not May, so in a few days. So I try to again reinvent or revise this Cenos problem and based on this limit problem of limit and the process. So here the this starting point of a running competition or Rennwettbewerb, sprint we call it in modern terms, and this is the limit, the PQ. And here the Achilles and here the tortoise, and I mean this is half of the distance. So a distance between this and these 2 points, which is B, and the tortoise start from there. And as we all know, this by the time the Achilles reached the point B, the tortoise reached the point C, the half of the distance R by 2. And then again, when the Achilles reaches C, again the tortoise reaches D, R by 4 in the same time interval, and it goes on. As a result, how Zeno argues, the Achilles will never be able to overcome the tortoise. So that's a paradox. So there are 2,500 years people try to problematize or solve the problem of Zenon. So I'm not going into that. But then my argument is, if we discuss this problem of Zeno solely within the context of geometry or mathematics or a spatial science, we are not going to solve the problem because the space is infinitely divisible. So that is the foundation of this Cenos paradox. But at the same time, within the context of the science of dynamic, there is no aporia. Because, and this specifications like the Achilles reaches the point B at the same time interval the tortoise covers half of the distance of AB, and then it goes on like this. And both these movements have to be retardation. Retardation in a specific mode, which tend infinitely to the point PQ. So that specific mode of retardation is, as explicated by Zeno, is that you cross half of the distance always in the same time interval. That the distance you covered, the half of the distance you covered in the same time interval. So basically, the Achilles and tortoise have the same mode of retardation. The only difference is this tortoise starts from a point, from the middle, whereas Achilles starts from the beginning. So as a result of this, and both these runners retarding infinitely, or that is moving in retardation infinitely to the limes, which is PQ, whereby the S, that is the Schildkröte, that is tortoise, is always ahead of Achilles, thereby forming two different infinitely small magnitudes in the end in a pure continuum. So this is almost like the geometrical model we have discussed earlier, the Leibniz model. So there are two different infinitely small quantities, but that is not an aporia. It is an aporia if we think or conceive these infinitely small quantities in discretion. It is not an aporia if we conceive this infinitely small, still different magnitudes in a process, that is in a continuous process, a dynamic process. So that is my argument. So the point is, if you fix the limits in advance, there can only be a singular mode of retardation whereby a dynamic process tends infinitely to this given limits. Now, suppose if this retardation changes, so like it becomes more or less, that means the movement accelerates or becomes slower, what would happen? If it accelerates, then it's obviously, and both Achilles and the tortoise um, cross a longer distance, a very infinitely small increment, even then, this limit has to shift backwards. So that's the point. So any change in this singular specific mode of retardation will result into the shift of this limits. So I try to explain that in a few models, like the time and space incorporated, the same time interval, and this is, I mean, with only one runner, which is Achilles or maybe tortoise. So the same time interval, this is the r is the distance between these two points, and r by 2, and then r by 4, r by 8, and r by 16. And I just want to show this is the arithmetic expression adding from 0 to 1 by 2, 1 by 4, 1 by 8, 1 by 16 ad infinitum to 1, which is the distance between these two, and which is the limits here. So here, the two possibilities of representing the change of retardation. If it accelerates, that means this r by 2 is covered in a lesser time, in less time, that is t minus delta t. Delta t is an infinitely small time entity, and t minus t, delta t1, etc. And this limit, so this is a kind of not acceleration, a change of retardation. That is, the retardation becomes smaller. So this limit will shift, the a, b will shift to a dash and b dash. And this is the spatial representation where t, the same time interval, well, r by 2 plus r. So the small increment in the spatial distance. So in that case also it will shift to outwards. And same way, if it is t plus delta t, so that means retarding more towards, I mean, a kind of increment in the retardation, then it will shift inward, and or r by 2 minus delta r, etc., etc. So the point is, this limit, which is a static, a discrete entity, as against a continuous dynamic process, still emerges from the process. So that's my argument. And if we fix the limit in advance, which is the standard procedure in differential calculus, then there is only one possibility, it's one mode of movement, which is a one mode of retardation. Any other mode of retardation or any change in that mode will set a new limit. So the limit has to emerge from the process. So this is another, I mean, old model, one the proto form of this movement in geometry by Nicolas von Cusa. I think it's on De Conjecturis or De Docta Ignorantia, I don't remember. And here the tangent, which is AB, and the circles, and at C and at a circle. And when this circle is enlarged, or when the diameter of the circle increases, so this periphery of the circle, which is enlarging, becomes straightened and reaches and coincides almost with AB, but it will never coincide with AB because it has to be a part of a circle, and a straight line and a circle are axiomatically different. So that there should be an infinitely small difference, but then for Cusanus, in a metaphysical principle, there is a coincidentia oppositorum. So these two opposite forms will coincide in God, and so that is metaphysics. Now this movement in geometry, that this process of infinite enlargement, if it's a dynamic process, and it tends to a static limits. So here also the same process and limit you can see. This is a static limits, which is a tangent, a given discrete entity, and a dynamic enlargement of the periphery of the circle. So this is another example given in the Docta Ignorantia. So a square inscribed in a circle, and if the sides are multiplied infinitely, and this will almost reach the form of a circle. And this form of circle is the static limits, and the multiplication of the sides forms the unending dynamic continuous process, and it will not only tend to this limits, which will never reach the limits, but still this limits emerges from this process. So I just want to show in all this all early models of process and limit, you will find the same principle. So, and another problem of all this representation, because, and in the mathematical sciences, in mechanics or optics, the mechanical or optical phenomena are represented geometrically. So for all the practical purposes and calculation, that would work. So this is a normal, like a diagram in any civil engineering classes. So a beam supported by two pillars with a distributed load and point loads, and this is the bending moment diagram. The problem is, and if I observe quite in a very naive fashion, these are only geometrical representations. These are not mechanical representations or mechanical models. So we cannot walk over these lines, and this line cannot carry any load. And these are just lines and not actual pillars. So these are all vectorial representations. And another interesting aspect is there is a historical transition from the mathematical sciences of the early modernity into material sciences. And as a result of which, the mode of representation changed. And as you know, the classical mechanics is entirely, you can represent in different vectorial models. And so the force was primarily represented in vectors. But then with the advent of material sciences, there is a transition from the vectorial representation to scalar representation. So a mechanical movement or a force constellation in a static structure or a dynamic structure can be represented like this in vectors, but then not pressure or temperature or viscosity or density or all these properties of material. They are scalar quantities. I'm actually working on this with one of the area of my current research. So, to the final part of my presentation, this is the method I've been deploying in my research, which is developed by Martin Kemp, an art historian who studied science first in Cambridge and then moved into art history. So always swings or between science and art. Martin Kemp published nearly 25 invited articles in Nature between 97 and 2000, where he introduced the concept of the structural intuition as represented in astronomical models of Kepler, for example, or the geometrical models of Descartes, Newton, and also the plastic art, sculpture, and architecture, and also anatomy and all. So this is a kind of very wide, versatile, domains where the structural intuition. I mean, the principle of structural intuition. That's what I'm interested. So then it was published in an edited volume, or not an edited volume. It's a collection of essays from Oxford University Press. It's Visualization, the Nature Book of Art and Science. So in the introduction, typical of Martin Kemp, very clear and coherent language, but quite complex if we analyze that. So the major argument of Martin Kemp is that there is a resonance between internal intuitive structures and external phenomenal structures. And as demonstrated in every design process by an architect or an artist, or the inventions in astronomy or geometry or optics by the great philosophers and the scientists of early modernity, and also the modern age, the late modernity. So I believe, as will always be apparent, that the deep structures of intuition with which we have been endowed by nature and nurture stand in a non-arbitrary relationship to definable elements in the structure and the behavior of the physical world. The structures of the external world within which we need to operate are those with which the internal structure of intuition has been designed to resonate, continuously reinforcing and retuning themselves in a ceaseless dialogue of matching and making. Why I'm introducing that in my talk is because I'm not going to elaborate on this, which is not possible, and for which I need a different presentation. In my next monograph, I've been working on this for a long time. So what I tried is, first I suggested to Kemp that because most of the models which he explained in his essays and later in this book are static models, because he's an art historian and the art history has works predominantly with static or plastic models. And I suggested that this could be applied to dynamic models. So then he started working on it, and there's a very interesting example given in this introduction, which I haven't quoted here, which is the playing football. So when you in a penalty kick, or better than that, a 30 meters kick, or in the play altogether, how the player can determine the movement of the ball when it approaches and when he kicks it back, uh, and the various factors, the surface friction, and the air friction, and the spin, and the elasticity that depends on the air pressure within the football, and many other factors, and plus the whole mechanical movements. So this for Martin came a clear demonstration of the resonance between internal intuitive structures and the phenomenal structures, because there should be a resonance. Otherwise, a football player cannot accomplish a proper penalty kick, or any kick for that matters, or passing of the balls, or anything, or headers even. Yeah. So, and without thinking, and this is purely a pre-verbal, purely aesthetic handlung, that is action. Yeah. So, and of course, there are a lot of other things, and I, in fact, in my recent research, which will be published soon, I try to develop a compository form of structural intuition. My argument is like, just like this football, playing football, you have to take into consideration the vectorial and the scalar forces, the forces that has to be represented through vectors and as a scalar entity. So it's a compositional structural intuition incorporating mathematical, mechanical, and the material. So now applying that compositional structural intuition into this process and limit problematic, I think for example, a paradox like Cenos paradox remains a paradox within the context of geometry, or the mathematical space, or the geometry, but not in the dynamics, not in the mechanics. Why? Because these are two different structural intuitions. So we have to shift from a geometrical intuition, which is based on the infinite division of the space, into a temporal dynamic intuition, where you have to intuit an infinite retardation of the movement that should solve even this aporia. And though the result will be a bit bizarre, like finally Achilles and the tortoise will remain in an infinitely small motion, almost like static figures, I mean frozen, and still not reaching the limit, and which is not perceivable at all, because we cannot perceive infinitely small distances. But still, in the theory, if it's a mathematical, dynamical, and material intuition, and material in which imparts reality to this actual process, and we can clearly see how this is possible. Okay, this is, I'm not going to explain this. This is one example Martin Kemp gives, the phases of splash, other Worthington's photographs, which he uses for to show how this splash photographed with a very high-speed camera changes its shapes and forms depending upon the viscosity of the fluid and the shape of the object that falls into it, etc. Right. And finally, this process and limit, I mean, the limit evolving out of the process, can that be applied directly, or more or less directly, to the science of mechanics, to the static and the dynamic? So this is just an attempt which I tried some 10, 15 years back in a monograph on the nature and structure of forces. Like normally we consider this, I mean, a beam between two pillars, and I mean, as we know, the gravity acts on all the bodies. It's a constant force that creates finally the dynamic out of the static. But as long as this remains static, we don't really think that there is a dynamic within it. So it's again the Leibniz concept that static, Ruhe als unendlich kleine Bewegung, the static as an infinitely small dynamic, or the similarity as infinitely small dissimilarity, etc. So these points, K and L, which normally we think static, are they actually static, or is there an infinite process of retarding movement tending towards certain limits? And those limits evolve out of the movement itself. So the movement determines the limit, but still that limit defines the static of the forces and not the movement. So any change in that movement, whether these limits are crossed or invalidated or um, shifts to inwards or outward, depending upon compression and the tension, the structure might sag or collapse. Yeah, so it's purely in the field of civil engineering. This is the footing and the shear force. I mean, more than this bending force, the shear force, we firmly believe that it's a pure static, and at the moment of its failure, that shear failure, there is a dynamic. So now, again, in accordance with Leibniz, there cannot be a sprung, a jump from a pure static to a dynamic state. There should be an infinitely small dynamic process tending towards certain limits, static limits, and those static limits define the static of the structure. But when those limits shifts, the failure occurs. So this is a different way of uh, perspectivizing the complex relation between static and the dynamic based on this, the principle of limit emerging out of the process. Yeah, that's all. And of course, this is I'm ending nowhere, so I'm just trying to revise what I've done earlier, and maybe I'll continue that in my fellowship in Constance. Thank you.